In this video, I'm going to find the magnetic field strength of a solenoid. If you take a solenoid, how much magnetic field it's going to produce. That's what we're going to talk about in this video. Now, we know that by using a right hand rule, a current carrying conductor, we can find the magnetic field direction by using the right hand rule. So here, assume that this is a loop. Here is a loop. It's a loop of conductor. Okay, so based on that, here the dot indicates that current is coming towards you. The cross indicates that current is entering into the loop. So basically, you take the half loop. This is a half loop. Loop is on the YZ plane basically. Okay, so if you take this as x-axis, that's y-axis and z-axis. So the loop is placed on the y and z-axis. Z-axis is coming towards you, so it's a half. So here is a conductor or current coming out. So if you look at the current coming out, the magnetic field direction. So by using the right hand rule, the magnetic field direction is going to be something like this. Okay, that's the magnetic field direction. So here, that's the magnetic field direction. Here is the magnetic field direction. Coming down. If you look at the bigger loop, or if you look at the smaller loop, it's going to be something like this inside the conductor, inside that loop. Now, in the second case, I took 3 loops, equal distance between all those three loops. Now, if we consider inside the loop, here we'll see magnetic field going straight inside the loop. When it comes to the outside of the loop, you see here you have 3 points. All these 3 magnetic fields are going to be sum of those 3 magnetic field vector sum of those 3 magnetic fields are going to be 0. So finally, what I'm saying, there is lots of magnetic field inside this coil. Okay, this coil is called solenoid. We're also going to refer this as inductor in the future, probably not in this chapter, it's going to be in the next chapter. So we can represent this as an inductor. So if you look at this solenoid, the magnetic field inside this solenoid are straight lines, lots of magnetic field inside this solenoid. But when it comes to the outside, the magnetic field is going to be 0. This inductor or solenoid is approximately equal to capacitor in your electric field. If you remember, you see you have a positively charged plate and negatively charged plate. There is always electric field here inside this, in between the plates. Anywhere in between the plates, we know that electric field is constant. Same way, anywhere inside this coil, here or here or here, the magnetic field strength is constant. So inside this coil is anywhere the magnetic field strength is constant, but outside the magnetic field strength here is 0 outside of the similar to the capacitor. So I can compare this with the capacitor, the solenoid or inductor. Now my goal is finding the magnetic field strength inside this solenoid or inside this inductor. I can use the Amperes law. I posted a couple of videos based to find out about the Amperes law. Please watch them. So closed integral of b times ds equal to, what is Amperes law? Closed integral of b times ds equal to mu naught times I enclosed. Okay, what is ds? So here I'm going to find the closed integral of this closed loop. Okay, so here ds is the smallest distance. This is the smallest distance. I'm trying to find what is the magnetic field strength produced by these conductors or around these conductors. We know that outside is 0, so we'll end up having inside magnetic field. So now here I enclosed, can I write that I enclosed is nothing but I have how many number of conductors? 1 2 3 4 5 conductors times I, that's our total current, right? So instead of 5 I'm going to use n number of conductors. So closed integral of b times ds equal to mu naught times n times I, where n equal to number of turns or number of loops, and I equal to current in each loop. Current in each loop. Now our goal is finding the magnetic field of the solenoid. So closed integral of b times ds equal to mu naught n times I. So the integral of this is nothing but L. So if I take this length is L. So b is constant anywhere, times ds equal to mu naught n I. Closed integral of ds is nothing but b times L times mu naught n I. So magnetic field produced by the solenoid or inductor is nothing but mu naught times n times I over L. L is length of the solenoid, n is number of turns, I is the current. In your textbook probably you will see Ni, where n is number of turns per unit length, number of turns per unit length. Okay, this is the magnetic field produced by the solenoid. Thank you.